If I were to roll a die, what number would likely appear face up? You probably saw this question as a trick question. Each number has a 1 in 6 chance of appearing, therefore any number can come up. Well, if that's the case, then how do we obtain any amount of information from something that's so seemingly random? Is there a conclusion we can draw if we want to learn about every dice roll in history? Well, let's do an experiment. So take your average 6-sided die. I have what a picture of a 6-sided die looks like right here in the corner. Each side has a 1 in 6 chance of appearing. Okay, so I'm going to roll a die 4 times, and I'm going to call that one sample. So let's say my first sample, I end up with a 3, a 2, a 3, and a 4. The average of that sample is 3. So in my second sample, I roll a 1, a 4, a 2, and a 3. My average in this case is 2.5 or 2.5. And then in my third sample, I roll a 4, a 6, a 5, and a 1. My average in this case is 4. So I'm going to repeat this over and over so I end up getting 10 samples. And here's a bar graph of my results. For each graph, I will always look at which averages frequently appear out of the 10 samples, or the tallest columns, and the general shape of the graph. The shape is hard to tell at the moment with this graph, but I notice that I can at least answer which columns are the tallest. I have 3 samples that have an average of 3.5, so that was my tallest column. And then my second tallest column is 4. Therefore, I have 2 samples that have an average of 4. And the remaining 5 samples are spread out. Now, because I don't have any kind of distinguishable shape or pattern, perhaps I didn't continue my simulation long enough, because 10 samples is relatively small. So let's repeat this process so I get 20 samples of 4 rolls. Here's the graph of 20 samples. As mentioned before, I will be looking at the tallest columns and the shape. Notice that my average of 3.5 shows up the most, with 4 samples having it. Now, as for the shape, I can see that averages on the left side, in these numbers right here, they're starting to go up. And this is different from what I saw in my graph of 10 samples. So now there's a bit of a hump, kind of like this. There's a bit of a hump in the middle numbers between 2.5 and 4.5. It looks like there's more of a pattern. So I'm just going to write that in the shape. There's a curve in the middle. Will this continue if I try to get 100 samples? So at this point I programmed a model to generate a random simulation and graph of 100 samples. Here are the results of that simulation of 100. For columns, I continued to have 3.5, with the most samples with 18. And let's talk about the shape. I also see the hump in the middle since I've been getting averages here more so than the averages on the ends. So in other words, the frequency goes up as the averages move closer to the middle. However, while I'm not getting the numbers at the ends as much as the ones in the middle, they are still appearing. So let me draw the general shape of what this distribution looks like. I'm going to use a different color. So does this look familiar? It's a bell-shaped curve that's peaking in the middle. So it looks kind of like the normal distribution. Perhaps I will give you the graph of when I have 200 samples to confirm the shape. This is my last graph of the simulation, the 200 sample graph. The tallest column remains consistent at 3.5. And that remains unchanged through all of the past simulations. And besides the column at roughly 2.75, the graph has become more symmetric, with the general pattern remaining true. A big bell-shaped curve around the middle and dropping sharply at the tails. So let's make note of that in the shape. Because this is similar to the graph of 100 samples earlier, but the pattern more closely resembles the normal distribution, but it has become more symmetric. This dice roll simulation is an illustration of the Central Limit Theorem, which states that as the number of samples increases, as well as the sample size, but we didn't actually change the sample size at all, it still remained at 4, the distribution of sample means more closely resembles the normal distribution regardless of the distribution of the dataset. If you remember, the roll of a die has a pretty uniform distribution as any number 1 through 6 has an equal chance of appearing. However, when I start increasing the number of samples of dice rolls, then I compute the sample means, I find that the distribution resembles the normal distribution. The more samples, the stronger the bell-shaped pattern. So why is this important? This theorem holds regardless of the distribution of the data set. That means, for example, if I were to try and figure out, let's say, the average number of text messages that the entire population sends out per day, I can make a reasonable guess by gathering groups of people, getting the average number of texts, and then repeating the process until I have a sufficient number of sample means of text messages. And the number of text messages is a pretty random distribution. Any person can send any number of text messages at any given point in time. In fact, because I will not only be able to make a reasonable guess or an inference on the average, I will also be able to guess the standard deviation, since I will roughly know what the distribution looks like. And so by understanding this theorem, we can now learn a great deal of information from data that is seemingly random.